Okay. If anyone want, could any one of you or someone turn on their camera, because right now with no camera on, I'm talking, to an empty room again, and then which I can predict my energy level would drop. Okay. Hi. Yeah. Yeah. I find that the difference between 0 audience and 1 audience is actually huge. Okay. Thank you. So today we're going Today we're going to start talking about the postulate of quantum mechanics. Okay, and this is probably the next 3 lectures is probably the most important 3 lectures. And then if you're a genius, okay, after these 3 lectures, you can derive the entire quantum mechanics system, and you don't need me anymore. But for average person like me, or well, probably some of you, okay, then if we understand this part, then it's actually much easier for the future class. Okay, so from previous lecture, we build upon the idea that electron can be wave, which is proposed by De Broglie, trying to explain the hydrogen atom emission spectrum. And then from there, we kind of say that, okay, because it's a wave, you kind of need a wave function. And then for wave function, because it's 1 electron orbiting around 1 nuclear, so it's hard to write down a wave function, wave equation like the mechanical wave, right? Mechanical wave, you have molecules interacting with nearby molecules. So there we start to say, okay, maybe you can use the energy to describe the entire system and then to build a wave equation. And at that time, okay, we start with the plane wave, and then write down this Schrodinger equation, which this part represents energy, this part represents the kinetic energy, which is this part is momentum, and then this is the potential energy. Okay, and then at the end of last class, we kind of very quickly show you guys that if you apply this to the hydrogen atom, where you replace this potential energy to the Ke squared divided by R, okay, the Coulomb's law, then what you can get is that you solve by using the boundary condition. You can see the eigenvalue, which is energy level, actually correspond to the hydrogen atom emissions spectrum. So that's a very happy coincidence. And then at the time, okay, when we solved that, we actually didn't know the meaning of the wave function. We didn't know the meaning of, well, we didn't know, basically we know nothing other than, okay, there's a wave and then there's a wave equation, so we solve it mathematically. So today we're going to dig into a little bit more detail to discuss, okay, what this wave is, and then how we can apply it in quantum mechanics. So as I explained before, the entire physics, chemistry, they're built upon experiment. So when you, okay, at this point, we already used 3 experiments, right? The black body radiation, the photoelectric effect, and then the hydrogen atom. And then we arrive at here. So in order to go further, you actually need further experimental proof, okay, to show you that maybe there's a connection between the wave function and then some measurable experimental result. Okay, I don't know how many of you noticed that in the YouTube playback list, other than the lecture video, there's actually one more video showing you that the experimental result of electron Young double slit experiment. Okay, the experiment was actually done very beautifully in I think it's 1926 or 1927. The idea is that, okay, we say that electron is a wave, then how about we do a typical wave experiment? Right, the first time people discover light is a wave is through Young double slit experiment. So how about we construct electron double slit experiment? So what you can do is that you can have electron here, a lot of electron, and then they go one by one, and then first slit is to control the direction of your electron, right? Because some of them going this way, some of them going that way. Only the electron going straight can go through. And then the hole is made small enough, just like what we did in Young double slit experiment, okay, to make it a point source, a point wave source. and then you have two very narrow slit again, just like young double slit experiment. And then there, okay, in your homework, you will be asked to show how narrow this slit is. Okay, how narrow this slit has to be. And then there's a screen here trying to detect, okay, trying to detect where the electron land, right, where the electron lands. So there could be many, many electrons, and then you try to see where they are, okay. And then, so I'll try to play the video here on the Zoom by share screen, but from my previous knowledge, the share screen function in Zoom, the video, they have a weird coding section that it will not be very smooth, but let's try to do it here. Okay, if it's not clear, then you guys can go to the YouTube playlist, and then, it's the same video.
Now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the bibosom, thus creating a uniform distribution without any interference when accumulated. Under such condition, do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible.
Okay, so if you guys want to watch that video again, you can watch it on YouTube, and we have the link in the playlist. Let's describe what this experiment looks like. Okay, obviously at the very end of the frame, what you see is that there's interference pattern, right? Interference fringes. That the electron looks like this. The distribution of the electron looks like this. Okay, so this is the final image. But then when you look at individual electron, what do you see? Like at the beginning of the video, when you're looking at individual electron going to the screen, it looks like almost like it's going random. Right? It's like you kind of can't predict where it goes unless you collect a lot of electrons and then you start to see statistical behavior of these electrons. And then this experiment is actually done in the sense that they're only sending one electron at a time, so that you can kind of exclude the effect of electron-electron interaction. Okay, so you can assume that all the electrons are obeying the same wave function, and then you're making detections all the time on this screen, and then all these electrons are identical. Okay, actually that video is not made for science purpose. If you look at the watermark there, it's actually by Hitachi. It's a famous Japanese tech company. So Hitachi made this video to showcase the performance of their single electron source. Okay, so the point is that their experiment went for 30 minutes, and then you can still see the interference fringes, which means that for the past 30 minutes, all the electrons are the same, and then they obey the same equation. Okay, so that's actually the purpose of that video. But then, fortunately, that can also be used for educational purpose. Okay, so the first takeaway here is that it looks like there's some statistical behavior of electron when you have a lot of them, right? When you look at them, when you look at the number of electrons at each spot. And the second is that when you look at individual electrons, it looks like they're random. Like when you can't really predict. Let's say I'm sending one more electron here, and then you can't predict where that electron will land. Okay, you can't really predict. You can say, okay, it has to land here because A, B, C. You can't do that. Okay, this is different from the classical mechanics. Okay, when you know the force, you know the initial position and speed, you know where the electron will go. Okay, and then the third thing is that when electron comes here, although we say electron is a wave, but then when you remember that video, electrons are lighting up individual spot on that screen, right? So it's like one spot shine up and another spot, another spot. So when you detect the electron, it looks like electron is particle. It's not like the electron is a wave and then spread out over the screen. When you detect it, you detect individual electrons. Okay? So what we can conclude from this experiment is that a reasonable argument here is that the electron, individual electron, when they come from the left to the right, their behavior, or their motion obeys a wave function, because only wave function can produce interference pattern. Okay. And the second thing is that when you actually detect individual electron, the electron collapses into a particle. Okay, collapse into a particle where you have this individual shining spot on the detector. Okay, so imagine, okay, if you do this experiment with classical wave, then what will happen? With classical wave, then you're shining a wave here, and then if you dim the wave to a level that's so low, what will happen is that not individual spot will shine up, but instead this wave pattern will be become darker and darker globally, okay, and you will not see individually if that's a mechanical wave. So if someone tells you, okay, if someone tells you quantum mechanics is just to make electron into a wave, that's not the correct description, because if electron is just a wave, then you will not see these particles. You will not see this individual detection spot in this experiment. And the same thing is that if someone tells you, okay, electron is just particle, that's also wrong, because if they're just particle, then you wouldn't see this interference pattern. Okay, and I know this sounds a little bit weird. It's like, okay, then when did I decide it's a particle? When did I decide it's a wave? It sounds like arbitrary, like when I need it to be a wave, it's a wave. When I need it to be a particle, it's a particle. So that's why we actually need the quantum mechanics postulate. Okay, with a field postulate that is kind of general, then you can formulate the entire quantum mechanical system to describe this experiment and many other experiments that's similar to this. And then the end result is that they all agree perfectly between the experiment and the theory. Okay, so any questions regarding that? Electron experiment? Okay, if no, then we can start with the postulate of quantum mechanics. So the first postulate, you guys can look at the notes, notes page 2, there's postulate 1. Okay, so just to save time, I'm not writing on here. The postulate 1 is a very simple one. Postulate 1 is saying that the state of a quantum object or quantum system is completely specified by a wave function. Okay, by a wave function. So your system, for example, electron here, is completely described by a wave function. Okay. It's kind of like saying that everything is a wave, but put them in a nicer language. Okay. Postulate 1. I think we probably don't have questions here because we've been talking about this for the past 2 lectures. Now, let's talk about postulate 2. Okay, postulate 2. Postulate 2 is widely introduced in most of the quantum mechanics textbook, and then actually it's a little bit redundant, but we'll go over here. So what is the easiest way to describe this behavior here? The best way, probably the easiest way, is that, okay, there's a wave amplitude, which is just like the Young double slit experiment of light, right? But then instead of the light shining, instead of light, okay, lighting up the entire screen, you see individual electrons coming, and then they appear randomly. But then when you have a large number of electrons, then you start to see this statistic pattern, right? So you can kind of start by looking at this and then this experiment, you can kind of think that maybe this wave describes a probability behavior, right? Maybe this wave describes a probability behavior that all this amplitude, it doesn't tell you, okay, it doesn't tell you exactly the electron, okay, will go land here, land there, no, but it tells you the probability of the electron coming here, okay? And if that's the case, then that kind of explains this experiment that when you are looking at individual electron, you can't predict where they go, but then when you look at a large number of electrons, then you start to see fringes. Okay, so the postulate 2 is to explain what this wave function means in experiment. And also one thing we have to know here is that if you look at the Schrodinger equation, okay, there is a complex number here. So that the Schrodinger equation is a complex number equation, so naturally the solution could have complex number. Right? It doesn't have to, but it could have. Okay? So this is a complex function. Now, if per psi, the wave function is describing a probability, okay, it's describing the probability. This is what we see in the experiment. The electron coming a little bit random, so it's probability. Then does that mean the wave function itself, the amplitude of the wave function itself, gives you a probability? Probably not, right? Because if you think about probability, the probability has a range from 0 to 1. Right? 0 means no probability is 0 of finding an electron somewhere. 1 is that you have 100% probability of finding electron somewhere. Okay? So probability is a real number ranging from 0 to 1. But wave function here is a complex number. Okay? It's not a real number, it's a complex number. So you cannot link this wave function directly to probability. Okay? So what it is, really it is that it's just like in the situation of light, right? The wave is the electrical field, but then when you detect the intensity, which is the square of the electrical field. Okay, that gives you the interference. So here is the same thing. You have a wave function, okay, and then your wave describes the complete system. The amplitude square of your wave gives you the probability of finding the electron. Now let me put it in a more let me have this in a more specific way. Okay, so there's the probability. The postulate 2 is that the probability of an electron, okay, showing up in position from R to R plus delta R. Okay, from R to delta R, for example, it could be a small place here, a small interval here. The probability of electron showing showing up in between r and r plus delta r, this small interval, is is the amplitude square of your wave function multiplied by the length of your interval. Okay, so what it is that it's a probability density. Right? Think about it. If the wave function is a plane wave, it's plane, okay, a constant, then if your interval is larger, then it means you have larger probability of seeing an electron in this area, right? Because you're detecting more. You're accumulating in more areas. But then if your interval is much smaller, then of course you will see less chance of electron falling into your interval, right? Because you're naturally detecting less areas. So the wave function amplitude square gives you probability density. Okay, density. And another way to explain this postulate 2 is that if you want to find the electron, let's say electron showing up in the area, let's say X belong to A, B, right? Let's say this is X, and then you have A, you have B. Okay, you will know the probability of an electron showing up between A and B, okay, between an interval, is, you can write it as probability AB equals to, because this is a probability density, so to find the probability, you just integrate the density. From A to B, right? From A to B, because each small interval represents the probability of the electron showing in that small interval. And then when you sum them up, then you get the total probability of finding the electron in the interval between A and B. Okay, any questions here? So everyone finding this fine, like treating the wave as probability? Okay, if no question, then let's proceed with some. Let's see what's the consequence of having this postulate, right? What's the consequence? So if we say this is a probability, and then we know that the probability has to be bounded between 0 and 1, right? 1 means you have 100% probability of finding an electron. Then a natural conclusion of this is that, let's call it note 1, or 2.1, 2 is the postulate 2, is that if the system is describing one electron, then the probability of finding that electron in the entire space must be 1, right? Because there's one electron. Okay, there's one electron. So there's a normalization condition here. Is if, let's say, this direction is x, and then you're sending one electron, and it has to be somewhere here. So if I try to find that electron between minus infinity and plus infinity, okay, minus infinity and plus infinity, according to postulate 2, this gives me the probability of finding electron between minus infinity and plus infinity. Basically saying that finding an electron on the screen. And this probability has to be 1, right? Because there's an electron there. It has to be a 1. Okay. So this is called the normalization condition of the wave function. And the reason for this to happen is that previously this is just a wave function, but now you're giving it a physical meaning, saying that it's a probability of finding the particle, right? And then because it's a probability now, it has to be bounded by 0 and 1. Okay, does that make sense? If the integration from the entire space is less than 1, what that means is that you're losing the electron, right? You're sending one electron out, but somehow it's blocked by something. Okay, so that means your experiment has something wrong. Okay. Everyone okay with this? Okay. Now, the second thing that let's talk about is, now if we say, okay, this is a wave, electron is described by a wave, and then the wave function has a meaning of probability, then let's try to use this postulate and then to describe some of the easiest situation in classical mechanics. Okay, classical mechanics, and see how things turns out. And let's see, the easiest situation should be there's a particle sitting at position x, right? Not moving, just sitting there, right? I can't imagine a thing that easier than that, right? So let's say you have an axis x, and then this is 0, and then your electron is here, x1. Okay, your electron is here, 100% here. Okay. Now, this is very easy to describe in classical mechanics. You just write, okay, the position x of the particle at any given time t is x1. That's classical mechanics. Now, in quantum mechanics, when you say that the electron is a wave, then what is a wave function looks like for a static electron? All right, that's a very natural question. It sounds very simple, and let's take a look. Let's take a look. Now, what do we really mean by electron is here? What it means is that if you're trying to find electron, at position x not equals to x1, then your probability of finding the electron should be 0, right? Should be 0. That's the meaning of saying electron is at position x1. You cannot find electron at any other position. Okay, you cannot find it at any other position. So this gives us psi x not equals to x1 square equals to 0. Okay, equals to 0. And next thing is you say, okay, then what about when you're at x equals x1? What is the amplitude of your wave function? Right? What is the amplitude? Now let's look at it in this way. The way to look at this is that let's say you're trying to find electron between x smaller than x1 plus delta x larger than x1 minus delta x, right? You're trying to find the electron in the interval delta x, which include x1. Right? You're trying to find it in this area which include x1. And because we know that, well, we say that electron is at x1, so your probability of finding electron in this interval must be 1, right? 100%. Right, 100%. So you should always have integration of x1 minus delta x to x1 plus delta x always equal to 1. Right? As long as the interval include x1, then your probability of the electron showing in that interval, of course, is 1 because it's at x1. And this has to be true regardless how small your delta x is. Right? Your delta x can be extremely small, but as long as it include x1 in it, then it's still 1. Right? It still equals to 1. So this is kind of the idea of like calculus, right? When you give something to, when you let something approach to 0, okay? Now let's consider one very simple scenario, which you say, okay, if this is extremely small now, delta x is extremely small, then this integral is no longer meaningful at all, right? You can just write it down as right? Suppose the amplitude of your function is in the limit delta x goes to 0. Right? If your delta x goes to 0, then you're infinitely approaching this spot of x equals x1, so that the integration, which is the sum of this function at different position x, the integration is no longer necessary. You're just looking at this spot times the small difference, okay, of your delta x interval, and this thing has to equal to 1. Okay, this equals to this in the limit of delta x go to 0. Okay, now if you look at this, can you tell what the wave function is? The magnitude of this, the amplitude of this wave amplitude? If you look at it, it will be xt square delta x right? You just move the delta x is a variable, you move it to the right hand side, 1 divided by delta x. And this equation is correct as long as your delta x approaches to 0. Right? Your delta x approaches to 0, then this wave function explode. Right? This wave function explode. Any questions here? Okay, so what this wave function then, what this wave function really looks like is that if we plot the y-axis as the amplitude square of your wave function, and this is x1, then your wave function is 0 at all places, and then explode to infinity at x equals x1. Right? This is the only way that you can ensure that the probability of finding electron at all other places is 0, and then the probability of finding the electron at any places, including at any interval including x1, is 1. Right? That's the only way, mathematical way, to have it happen. Okay, so from here you kind of see that even the easiest situation in classical mechanics, when you say that the electron is a particle, when you convert that to electron is a wave, you have, at least some mathematical problem. Okay, mathematical problem. And when physicists found this, okay, when physicists saw this, you really can't calculate infinity, right? Because infinity can mean a lot. Like all this, x goes to 0, 1 over x goes to infinity. X equal to 0, 1 over x squared also goes to infinity. But then this two infinity is not the same infinity, right? One of them is approaching infinity faster than the other. So just saying that, okay, something is infinity doesn't fully describe the wave function. So here, what the physicist does is that they propose a function called delta function, okay, delta function to specifically describe this type of situation. And let's erase here. And the definition of delta function is that if there's a function that when x equals to x1, it goes to infinity, and then this function equals to 0 when x not equal to infinity, x not equal to x1, and then the integration of this function from infinity to minus infinity to infinity is always 1, then this function is called a delta function. Okay, this function is called a delta function. It's actually, you can see that it's actually set for quantum mechanics because the integration from minus infinity to infinity equals 1 is just your normalization condition, right? It's just your normalization condition. And mathematicians really don't like delta function, okay? Because they think it's kind of ill-defined. And actually, I agree with them because when you say delta function, in your mind, you think, okay, it's a function with a certain, when we say a function, usually to be a function that you can write it down, fx equals to something. But in delta function, actually, no. Delta function is a very general definition, and then many different type of function can actually approach delta function. And I will give you guys an example here. A typical delta function is that this is y, okay, this is x. And let's say there's area A, right? If y equals to 1 over A at x smaller than, if x is at x1 minus a over 2 and x1 plus a over 2, and then y is 0 at any other x. Okay. So see that the area of this function is always 1, because if you're narrowing a, then the amplitude goes up. So this function y, at the limit of a goes to 0, when it becomes infinitely narrow, the amplitude becomes infinitely large, and the area is still 1. So this function actually is a delta function. Okay, by definition, it's a delta function. And this is actually not a very good delta function because you can see it because it's a step function, right? On this side, it's from 0 to some value and some value back to 0. So it's not continuous, right? So this function is kind of not the ideal delta function. Okay, and in your homework you will see that in some Fourier transform, delta function can also be expressed in terms of Fourier transform, and that is usually a preferred way in some cases. Okay. Any question regarding the delta function and then electron at a certain position? asking question actually really helped this class because I can tell you my energy level here is very low. I talked to an empty room for 40 minutes now. Any question is welcome. Okay. So we finished one example, which is using the wave function to describe a very standard classical case that the electron is at a certain position, and then the wave function explodes. Okay, which is not a good sign. Okay, but anyway, that turns out to be okay, saved by Dirac function. Now let's look at a second example, because we say that okay, this is this is a wave, and then the amplitude of this represents a probability. Now let's look at, previously we looked at the simplest situation when we think about electron as particle, right? It sits some places. Now we look at the opposite side, is how about we treat it just as a wave, right? Then the simplest wave we can find, which is a plane wave, right? The simplest wave is a plane wave that it looks like this. And then if you think, okay, I don't want to solve the time evolution right now. I don't want to look at that. I just want to know what this means if there's this wave arrive at the detector at a certain time t equals 0. What that means? Then we can simplify this to t equal to 0. Just look at the spatial distribution here. Okay. So this is a plane wave, simplest wave. Now, according to postulate 2, the amplitude square of this will give you the probability density. Right, the probability density of finding the electron at position x equals to amplitude square of this. And then this is a complex number, right? Complex number, the amplitude square means that you are alpha. Let's say alpha is a real number. No, alpha doesn't have to be a real number. Alpha EIKX times alpha conjugate E minus IKX. Right? This is a conjugate of your wave function. And then alpha times alpha conjugate equals to amplitude square alpha, and then exponential ikx times exponential minus ikx is 1, right? It's 1, they cancel each other. So that what you end up with is that you have a flat distribution of your wave, right? So if you look at the real part of this wave function, which is a cosine, okay. But then if you really try to detect the wave, and then see where they are, and then you get a flat one, right? You get a flat one, and then the probability density here is alpha square. Okay, alpha square. So this kind of makes sense, right? We say it's a plane wave, and then it's really plane. Okay, nothing to complain about. This is where we start. Now let's look at how to normalize this, right? Because this is a probability, you have to normalize it. So if you try to normalize it, what you will get is that minus infinity plus infinity, the wave function amplitude squared dx has to equal to 1. Right? That's a normalization factor saying that, okay, whatever wave you are, but then the probability of finding electron between minus infinity and infinity has to be 1. Right? There's one electron here, and then I can find it. And if you do that, then you see that this integration is just alpha square integration minus infinity plus infinity dx, right? This is just 1. It's the integration of 1, okay, from minus infinity to infinity. And if you know what this is just alpha squared times x, right? The integration of 1 is x from minus infinity to plus infinity, right? Then this is plus infinity minus infinity, right? So you get 2 alpha squared infinity equals to 1. Right, so again we end up with infinity, which is a little bit weird, but then totally makes sense. So what this equation tells you is that if you put infinity on this side, then alpha squared equals to 1 over 2 infinity, and 1 over infinity is 0, right? It's 0. So that your amplitude is infinitely approaching 0. Let's not say 0. It's approaching 0. Okay, it's approaching 0. And this makes sense, right? Because what you're saying is that the probability of finding this electron in the entire universe is the same. And because the universe is so huge, then of course the amplitude of the probability of finding one electron at a certain place is infinitely small. Right, it's infinitely small. The way to think about this is that if you launch a rocket, and let's ignore gravity first, launch a rocket, and then let it fly in the universe, and it will not hit anything, okay, because the universe is so empty. Okay, it will not hit anything. This is the same idea here. Finding one electron in the entire universe, the probability has to be approaching 0. It's so rare. Okay. So now here we already say that okay, there's 2 scenarios which are easiest in classical mechanics. One particle at a certain position, well, it turns out the wave function explodes. The second one is the plane wave, which is the easiest for wave, but it turns out the wave function goes to 0. Okay. So later you will see that the reason for this to happen is that there's a gap between quantum mechanics and classical mechanics. You can't just say one approximate to another, and the difference here is actually made by the uncertainty principle. And let me make that clear here. What uncertainty principle means here. Okay. And for this wave function, does it have a certain momentum? Does anyone remember what momentum is in quantum mechanics? Anyone say anything?
An object in motion tends to stay in motion.
See the energy h bar omega, right? So what is the momentum? We previously say that momentum is h bar k. Right, this is from the Broy's assumption. Well, this is not from the Broy's assumption. This is from assumption of energy is h bar omega from Max Planck. And then when you apply for light, and then light, there is a relationship between energy and momentum, and then you can get the momentum is h bar k. Right? This is also how we get Schrodinger equations. This part, why this part is momentum. Right? It's because when you do derivative, you get a k out. Right? You get a k out, and then it becomes momentum. So for this wave function, what you can see is that there's only one k factor here. Right? It's a plane wave, one k vector. So for this wave, if I ask you what is the momentum, you can directly tell me, okay, it's h bar k, right? Because that's how we derive the momentum, h bar k here. So for this plane wave, you know exactly what the momentum is. The momentum is h bar k. What this also means is that the uncertainty of the momentum, uncertainty here you can think about it as that whether you can know this for sure or not, right? Here we know that the wave is propagating along x direction with a fixed wave vector. So the uncertainty of the momentum goes to 0 because you know the momentum is this. What is the momentum? What is the uncertainty of the position? Can anyone try to answer this? Give a guess.
What's K again?
K is the wave vector. K is defined as 2 pi divided by lambda, right? In classical mechanics, lambda is the wavelength, right? Okay. So if you have, so we already say that the probability of finding the electron in the entire universe is the same. Then what is the probability? Then what is the uncertainty of the position of the electron?
Is it infinite?
Yes, infinite, right? Because you can find it anywhere, right? You can find it anywhere. So if you use uncertainty equation, it would be like you do a measurement and then you minus the average. Average is 0, and then you square it, and then you sum the entire thing divided by n. Right? This is when you do experiment. This is the variance of your measurement. Okay. If you look at this, then you say, okay, the average is 0. The electron can be anywhere, right, from minus infinity to infinity. So that this thing, okay, if you do infinite amount of times of measurement, then the uncertainty will actually approach infinity. Okay. So this is just an example of uncertainty principle. If you have 100% knowledge of your momentum, then you have 0 knowledge of your position. Okay, 0 knowledge of your position. Now because we have this example now here, let's look back to the delta function. Let's look back to if I put electron here at x1. Okay, this is square x. And we know that x is at x1. Right, x is at x1. Now, then that means the uncertainty of position, of course, goes to 0. Okay, goes to 0. And what does that mean for the uncertainty of momentum? Now let's think about what momentum is, right? Momentum in quantum mechanics is bar k. And what is k? K is 2 pi divided by lambda. What is lambda? Lambda is wavelength. What exactly is wavelength? Wavelength is the distance you need to travel to repeat itself, right? So the wavelength comes from the fact that your wave is periodic. Then you have a wavelength. Okay? Is this function periodic? Is this delta function periodic? No, right? It have a spike at a certain position. So it has 0 periodicity. Okay? It doesn't have any periodicity. So that your wavelength is just unknown. You need at least one period to know your wavelength, right? Now you have no periodicity, so you actually don't know your wavelength. And if you don't know your wavelength, you don't know your k, and you don't know your momentum, right? So this one, the momentum actually goes to infinity because there's no wavelength in the delta function.
But if there's no wavelength, why can't you say like lambda equals 0? Or is that what you are doing?
So lambda equals 0 means that your wavelength is extremely short, right? Then it's actually looking like this, oscillating extremely fast, right? So that's different from saying there's no periodicity. Okay. And then later in Fourier transform, we'll talk about this later. You will see that if you convert the wave function from position to momentum, you actually see that it gives you that the momentum of this state is a flat distribution in momentum, which means that this wave function has infinite components of momentum. It has every momentum, just like this plane wave have every position. Okay, so the difficulty we see here, the infinite, the delta function we see here, coming from the fact that there's a fundamental limit, and that's the uncertainty principle. And we haven't officially introduced uncertainty principle yet. We'll talk about that later when we have all the definition of quantum mechanics. Okay, and the fact is that these are strictly true. Okay, although that you see the electron land somewhere in the detector, okay, but then the area it shine up is not infinitely small, right? It still has an area, right? If you really try to have electron land in this position with infinitely small uncertainty, then in quantum mechanics what you can show is that it will have this system has to have infinite energy, okay? And then then they actually violate the well, we don't have infinite energy in the universe, so that violate the common sense. Okay. Any questions for this part?
Professor, what are the units of the wave function squared?
Yeah, great question. Okay, great question. So let's look at here the normalization factor here. Okay, you see the wave function amplitude square times dx is length, right? Times length equals 1. 1 is dimensionless, it's probability. So the dimension or the unit of wave function square is 1 over length, or you can say 1 over meter. Right? So the wave function itself has a dimension of 1 over meter square root. Okay, does that make sense?
Yeah.
Okay, yeah, great question. Yeah, and then you can see that, okay, this is for one dimensional, right? If you are doing 3-dimensional, then this is dx, dy, dz, then it's become L to the third, right? Then you're 1 over meter to the third. Okay, other questions?
I noticed that you put it as a postulate that the probability is the wave function squared.
Yep.
Did people just sort of like try it out and see if it worked with the experiments? Or is there like an actual reason why it is the wave function squared?
Yeah, that's a great question. Okay, because so first that's really just a postulate. Okay, it's in the official quantum mechanics. If you if you look at the textbook, that's not like Introduction to Quantum Mechanics, but just quantum mechanics. This postulate can be derived from the other 3 postulates, but still that they are postulate. They are not like They're just an observation of the experiment. And then this postulate actually raised a lot of questions, right? Like, what it's saying is that we are giving up deterministic entirely of quantum mechanics. Right? We're saying that the wave function, postulate 1 says the wave function completely describes the system, and postulate 2 tells you that this wave function just gives you a probability of finding the electron somewhere. Which means that when the electron, right, in that experiment, when the electron left the electron gun and then going to the screen, you actually don't know where it's going other than saying that, okay, it has more probability of going this place other than that place. And if you think about it, this is fundamentally, this really changes everything, right? If you think about it in terms of how we learned classical mechanics. Classical mechanics tells us that if you know the initial position, initial speed, and you know the force, you know the interaction force, you can predict everything afterwards, right? That's the scary part. That's that, at the Big Bang, okay, 13 billion years ago, whatever the initial condition there determines what we do here. Even determining that you're asking me this question and me answering you this question. And people don't like that in classical mechanics. And having this postulate, which looks weird, but actually, in my mind, really saved the modern physics, is that there's uncertainty here. Okay, there's uncertainty here that even you know all the initial condition, you know all the rules of quantum mechanics, of all the rules of physics, you still can't tell me, okay, where exactly would that electron go? Okay, so it fundamentally introduced uncertainty, just like uncertainty principle here. These two actually you can kind of derive each other. Okay, uncertainty principle and this postulate 2, or you can start from uncertainty principle and derive postulate 2. So postulate 2 is from Schrodinger picture, and then uncertainty principle is from Heisenberg's method. There are different ways, but then they all agree with each other. So that actually means that there's a huge uncertainty in the evolution of the material world. Right? You cannot no longer say that because I'm a god. Well, I guess this means the death of God. Right? So you cannot say, okay, there's a God who knows everything, therefore he or she can dictate everything. No, you cannot say that anymore because there's the postulate 2 or there's the uncertainty principle. Things are probability now. Okay, so it looks like counterintuitive at first, but then if you really believe that mankind is self-conscious, then you kind of have to believe this, right? Because otherwise we're saying that mankind are not self-conscious. Whatever we do is determined by initial conditions 13 billion years ago. So this one actually makes a lot of sense if you think a little bit deeper into this. Okay. Any other questions? Yeah.
So does the amplitude of the wave function itself not really have a meaning? If so, what is the meaning of the amplitude?
So you mean this one, right? Not the square, but just the wave function itself.
Yeah, because if you're squaring it, then no matter if it's positive or negative, as long as it's the same absolute value, you get the same probability, right? So
yes.
What does it mean for the amplitude to be negative versus positive? What's the difference?
Yeah, that's a great question. So we're actually going to talk about it next, in the next postulate. But what I can tell you is that the wave function, this is part of the reason that people don't like the wave function, is that because it's a complex number, actually you can't measure the wave function, right? Because all of your measurement instrument give you a real number reading. It doesn't give you a complex number. There's nothing come out as complex number. So in physics, as long as a physics variable is a complex number, that means it's not measurable. So wave function is not measurable. Unfortunately, it's not measurable. So then you have to wonder, okay, is wave function really necessary? Do we really need to introduce something that we can measure to explain things we can measure, right? And then this is a fundamental difference between Schrodinger and Heisenberg. Heisenberg just think this is redundant. It's ridiculous, okay? So he based from uncertainty principle and then from the fact that you can write down momentum as an operator. Okay, he starts from here and then derive this entirely different system, which is called matrix system. Okay, and then from in the history, what really happened is that Heisenberg is with the Niels Bohr Institute, and then they're a strong supporter for Heisenberg's theory. Okay, because it's kind of, if you look at it, it's elegant, right? Because it doesn't introduce anything that's not measurable. And then Schrodinger introduces, and so Schrodinger paid a visit to Heisenberg, and then they got into a fierce debate, and no one can convince each other. And then Schrodinger actually got sick, literally sick there. And then so I think it's 1 or 2 years later. I think it's either Fermi or Pauli, one of them, at the age of 22 or 23, proved that you can derive Schrodinger's result from Heisenberg's result and vice versa. So these two are actually the same. So it's redundant, but then it fully describes the system. And the negative and positive, if you think about this here, okay, we can. I'm actually saving this to the next postulate, but we can, since you asked, I can show you here. Individually, the minus and plus sign doesn't make any sense. But now think about it, if you're a double slit experiment, there are two waves arriving at the screen, right? Let's use the simplest situation. The first wave is e to the ik1x. The second wave is e to the ik2x, right? So at some position, this one will have minus sign, this one will have positive sign, right? So now if you say, okay, the entire system has a wave function of they linearly combine, right? Linearly combine, then if you measure the probability, what you will see is that you will see eikx1, eik2x squared. Then here it will make sense because at some places you have 1 minus 1 give you 0. Right? So a very important thing to detect, to verify that you do have quantum mechanics governing your system, is actually to do this what we call quantum interference. Right? Having individual wave, you can't really tell the difference, but having two wave, okay, they have one is plus, one is minus, and then you combine them, you see 0. Okay, so that's the meaning of that. Kind of show you that the wave, although you can't measure it, it's one of the mathematical way to describe quantum mechanics, and it works. Okay, great question. Other questions? Okay, let's quickly, since we're already here, we have 5 more minutes. Let me quickly introduce postulate 3, which is relatively straightforward. If you guys ever seen Schrodinger equation is linear, right? Which means that there's no wave function multiply wave function. It's a linear function. And so the postulate 3 is that if psi 1 and psi 2 are both possible configurations of the system. Right? Let's say you can prepare the system in psi 1. You can also prepare the system in psi 2. Possible configurations. Then you must have the linear combination of psi 1 and psi 2 is also a possible configuration. It's also a possible configuration of the system. Right? This is the same as any, the classical, well, not any, but the normal classical wave you guys learn, like water wave. Okay, they cross each other. Light wave, they also have interference effect, and you have them linearly. The linear combination of them is also a possible solution, and this is called in mathematics this is called linear combination, but in quantum mechanics it's called superposition. Okay, superposition, and one consequence of this superposition is the interference, quantum interference. So let's use this as example, right? So if you have the first configuration is a plane wave ik1x, what this means is that let's drop the alpha factor because it goes to 0. It's kind of annoying. So what it means is that the probability of finding the electron in the entire universe is uniform, right? It's the same everywhere. For wave function 2, ik2x, it's also uniform. It's the same finding electron, the same probability of finding the electron everywhere. Now, if your wave is now psi 1 plus psi 2, a linear combination, then all of a sudden there's interference terms here. You can do this calculation and then you will see that it's actually 2 plus 2 cosine k1 minus k2 x, right? K1 minus k2 x. So this gives you a probability of there's a normalization factor, I should say, proportional to. This one is not carefully normalized. Okay, so what you see is that two normally distributed function waveform, when you add them together, okay, now you can have some places, because cosine is from -1 to 1, some places you can have 0 probability of finding the electron. Okay, and this is the reason, why in the very first lecture, when we say that when you combine two 50-50 black and white electrons, the white electron can completely disappear. Right? The reason is exactly here, because when you add two things together, although individually they look like 50-50, individually they look like you all have a probability here, but then when you add them together, they can be off by a phase, a pi phase, and then you can have 0 probability, end up with 0 probability. Okay, so this is interference effect, unique for the wave, and then because we assume electron is a wave, then you also have interference effect here. Okay, and this is for the first 3 postulate, and then the next class we will introduce postulates 4 to 6, which is also very interesting, a little bit more difficult. Okay, and I'll stay here for 5 more minutes if you have any questions.
Thank you.
Professor.
Yeah.
So how do we know that, because before we had the statement that the integral over the entirety of space of wave function squared is equal to 1.
Yeah.
How do we know that's going to hold when we linearly combine with another wave?
Yeah, that's a great question. So what we do is that when you add these two together, okay, when you add these two together, you have to you just have to normalize it again. Okay, you can say that this is 75%, this is 25%. That's fine, but when you add them together, you have to recalculate this alpha and beta. There's a normalization factor here, n. Okay, and then you kind of have to do this for every wave when you combine them. And then it sounds a little bit complicated, but then later when we show that if these two are orthogonal waves, later we'll introduce this concept, then this becomes much easier. Is that you only need to, if they two are orthogonal, then you only need to make sure that the amplitude square, the sum of the amplitude square is 1. And we'll probably talk about this like next Thursday.